Here we have an example of using moments to analyse a problem that has two supports. In this case, we have got a beam, which in this example is a 1 meter ruler. Write that there. So it's a 1 meter ruler, and it's supported by two wires, one on the left here at a point called A, and one here on the right at a point called B. So there's a few other bits of information I've added in. You've got a weight of the ruler, which is 2 newtons, and there's also a 3 newton weight, which is hanging 0.3 meters from B. So I'm going to add them into my diagram. The weight is from the center, and that is 2 newtons. I'm just going to, in brackets, just mark it as the weight. I've also got this 3 newton weight hanging there. Now the distance from there to B is 0.3 meters, and the distance from the weight to the end is going to be 0.5 meters, because of course it's halfway along the ruler. So the weight goes from the center of mass, or the center of gravity, and it's a 1 meter ruler, it's a 0.5. I'm also going to sketch on the distance is the other way. So if that's 0.3, this will be 0.7. And of course, if that is 0.5, then that is also going to be 0.5 meters. So that's the setup, and I would always encourage you to draw the diagram. Now, how are we going to approach this? We are going to use the principle of moments, which I'm going to write down. That symbol means the sum of clockwise moments equals the sum of anti-clockwise moments. So, principle of moments, sum of clockwise moments equals the sum of anti-clockwise moments. And we all know that our moments equation equals force times distance. Okay, so if we think about it, the tricky thing with this is kind of how to start it. You've got 2 points. So what we do is we say moments about A. Now, so I should have said, in terms of analysing this, what we're looking for is there'll be a force, a tension in the wire holding this, and I'm going to label that force A, like that, and there'll be a tension in this wire, force B. We don't know force A or force B, and that's what we're going to use this to work out. So moments about A. Now the nice thing about taking moments about point A is if force A is at point A, because the distance is 0, force times distance is 0, it means the moment of force A at A is 0. And what you've got to think is, taking moments about A, you sort of treat point A like a pivot. This beam is hanging, it's balanced. So this question, this type of question only works like this if it's balanced, but we can consider it as something that could move. So if this string wasn't there, so if that wire wasn't there, it could move up and down. So moments about A, thinking about A as the pivot and B as a point that could move, you've got 2 forces here that are going to, in theory, sort of try and pull it down. So that's your clockwise moment. You've also got a force B, that's trying to pull it up. Now the moments are balanced, so it's not moving, but on their own, these two would pull it clockwise, and this one would pull it anti-clockwise. So sum of clockwise moments from point A, you've got the weight, so 2 newtons times by 0.5 meters, plus the 3 newtons times by 0.7 meters. that is going to be equal to the sum of the anti-clockwise moments, which is only force B. So that is force B times by 1 meter. So this is 1 Newton meter plus 2.1 Newton meters equals force B times by 1 meter. So 3.1 Newton meters equals force B times by 1 meter. I've deliberately left the 1 meter in there because if I then do 3.1 Newton meters divided by 1 meter equals force B, you can see the meters cancel and you get 3.1 newtons. Okay, so that's our moments about A. Now I'm going to have to come out a little bit to do our next bit. So moments about A has got us force B. So to find the other one, force A, I'm going to take moments about B. So you should be thinking ahead of me here. Pause the video, do what you need to do. Now, moments about B. Again, if you think of B as a point that is fixed, in theory, this ruler could pivot around like that. So you've got the 2 and the 3 newtons pulling it that way, which is anti-clockwise, and force A, which is pulling it up, that's clockwise. So they need to be balanced, which means what are we doing? Right, so at B, 0.5 meters times by 2 newtons. Sorry, clockwise moments first, which is the top one. So actually, it's force A times by 1 meter is equal to the sum of the anti-clockwise moments, which is 2 newtons times by 0.5 meters plus 3 newtons times by 0.3 meters. So force A times by 1 meter equals 1 Newton meter plus 0.9 Newton meters. Okay, so force A times 1 meter equals 1.9 Newton meters, and again that means force A is equal to 1.9 Newton meters divided by 1 meter. That gives me 1.9 newtons. Okay, now those of you that know your principle of moments know I've missed something. You know what it is? Principle of moments should be combined with this term. So what it should say is when balanced. That should always be in there. Okay, so don't forget that. So moments about A, we found force B. Moments about B, we found force A. Now here's your check. And I'd always suggest doing this first before you do this check. It will work out better because if you made a mistake here, this check won't work if you don't do this in full. The check is the total force is down to 2 newtons plus 3. So total down is 2 newtons plus 3 newtons equals 5 newtons. That's got to be equal to the total up, which is 3.1 newtons from force B and 1.9 newtons from force A. Just come out slightly, you can see all that. So total up is 1.9 newtons plus 3.1 newtons, and that also gives me 5 newtons. So they are the same. That's good. There we go.